Hello again. So we're back for our second lecture here. And so remember last time, what we did was we talked about time. And we talked about signals, which are functions of time. And we talked about vector spaces whose members are functions. And we had some, important examples of such vector spaces. And this lecture, we're going to continue sort of along those lines, talking about basically linear algebra, but geared towards the specific topics of interest for us here. Okay. Linear algebra. Okay, so last time we had these examples of vector spaces again, which were functions, and we kind of looked at a couple examples. And let me remind you what those were. And one example in particular had a couple of incarnations. And that was this example, f to the j, where j is a set. And so this, you remember, was by definition mappings from J into F, and we looked at this in particular for two cases: one where J was a finite set, and the other where J was the set of positive integers. And in this case, we showed that the vector spaces in a fairly natural way isomorphic to Fn, and then we saw in this case that essentially an element of this vector space was a sequence, and it's not even essentially, it just is a sequence if you define a sequence as being a map from the set of positive integers into F. That's a very good way to define what it means to be a sequence. And so, so what we want to do now is we want to think about, kind of what's the structure of these things as vector spaces. Okay. Now, if you're going to talk about a vector space, there's really only one thing that characterizes a vector space in the absence of any other kind of structure, and that's the dimension of the vector space. So, and what I mean by that is that if you have two vector spaces, what does it mean for those vector spaces to kind of be, equivalent or the same as vector spaces? Simply means that there's an isomorphism between them. The fact of the matter is the two vector spaces are isomorphic if and only if they have the same dimension. Now, dimension is something that we defined for, or that you defined in your linear algebra course for finite dimensional vector spaces. But we're going to think about dimension for infinite dimensional vector spaces, because those are the kinds of things that we're going to encounter most often. And it's not so much that we're interested in thinking super carefully about the abstractions of vector spaces of arbitrary dimension, but thinking about these things gives us some insight into some things about vector spaces like this, and in particular about vector spaces like this that are going to be useful for us later. Okay. So let's think about the dimension of a vector space. Okay. So previously in your linear algebra course, the dimension of a vector space was the number of vectors in a basis, and one of the things you would have shown was that any basis will have the same number of vectors, and probably that discussion was restricted to finite dimensional vector spaces, which by definition have finite bases. But that characterization carries over to arbitrary vector spaces in the following sense. So we can define the dimension of an arbitrary vector space as the number of elements in any basis. Okay, so that kind of definition of dimension carries with it two questions that you immediately have to ask, and that you know about in finite dimensional vector spaces, but otherwise you don't. And that is, how do you say number when that number is infinite? And can you still show that any basis has the same number of elements? So this definition is actually well framed. Okay, so both of those questions sort of hinge on saying what you mean by what's the number of elements in a basis. And so let's just talk very briefly about the notion of cardinality. And cardinality, so cardinality is a property of a set. So if you have a set, you can talk about the cardinality of a set. So I'm not going to, give a super careful description of this. You can do that and talk about these things which are called cardinal numbers. But that will take us way too far afield, and we don't need to go that far in order to be able to say the things that are useful for us. And so really all I want to be able to say is when two sets have the same cardinality. Okay, so I'm really talking about two sets, not the cardinality of a set, but two sets when they have the same cardinality. So two sets have the same cardinality, and the definition here is kind of both easy and opens up a whole can of worms if you dig into it deeply, which we will not. So for us, the definition is easy. And we'll just say the two sets have the same cardinality if there exists a bijection between them. Okay. So we say that a set X is one, finite, okay, if it has the same cardinality as some finite collection of numbers, say 1 up to n, for some n. Okay. So that's what a finite set is. And so, that agrees with your intuitive idea of what a finite set is. It's just a set where you can count the elements with some finite list. The other piece of terminology is countable. If it has the same cardinality as set of positive integers. Okay, so this means you can count the elements in the set, because for what this means is there's a bijection from your set into the set of positive integers, and so you can say what the first element of the set is, the second element of the set, and so on. So you can count the elements. It's uncountable if it is neither finite nor countable. Okay, so I guess I'm assuming X is not the empty set. Okay, and so for example, let's give some examples which sort of fit into these classes, just to kind of give us some understanding of this. And so these are things you have to prove. And I'm not going to do that here, but I'll just mention where you can sort of Google this stuff. The set of integers is countable. This is more or less obvious, because what do you need to do? You need to establish a bijection between the integers and the positive integers. Well, that's kind of easy to do. So let's say here's 0, here's 1, here's 2, oh, sorry. -1, 2, -2, and so on. The way you could do this is you could label this as being integer 1. This is being integer 2. This is being integer 3. This is being integer 4. This is being integer 5, and so on. And that establishes a bijection from the set of integers into the set of positive integers. You can show that the set of rational numbers is countable. Okay, and there's a variety of ways of doing this. Sort of one of the standard techniques for doing this is that you make a square with an integer grid. Okay. So I have a grid like so. Okay, so what I'm going to do is I'm going to walk through this grid, choose some arbitrary but systematic way of walking through the grid. And so what does that mean? So maybe what it means is I start at 0, and then I go here, and then I do this. Okay. So I walk through the grid. And in doing so, what I'm going to do is I'm going to assign to each grid point, or well, most grid points, a rational number. Okay. And so let's say that I call this the axis here, the numerator axis, and I call this axis here the denominator axis. And so as I pass through, here I'm going to, oops, sorry. Here I will assign the rational number 0. Okay, so I come up here and I'm at the point numerator is 0 and denominator is 1. Okay, so I then take the rational number 0 over 1, which is 0. Okay, and so I might double count things, and I can bookkeep that in a variety of ways. One is if I've counted it, I can just sort of discard it and move on to the next one. Okay, so then I move out to here, and the numerator is 1 and the denominator is 1. So that sounds like the number 1. Okay, so now I have the number rational number 1. So then I come down here and I have numerator 1, denominator 0. Well, that's not defined, so I just skip over that one. Okay. Then I come here and I get -1, right? So the numerator is 1, the denominator is -1. That sounds like -1. And then I just keep going like this. And then what you can show relatively easily is that every rational number is going to occur at one of these grid points. And it'll occur more than one. And if it occurs the second time and the third time and the fourth time, I just skip over it. So that's a way of establishing a bijection from a Q into the positive integers. Okay. So, this is kind of a sketch of an argument. You have to, kind of take this and turn that diagram into something rigorous. It's not hard to do. Okay. But I mean, there's other ways to show that the rationals are countable. That's one way. What about the set of real numbers? This is uncountable. Okay, so there's a variety of ways of proving this. One way is what's called, and I'm not going to go through it here. It takes too much time, and you would just have to sit with it anyway, all by yourself, to figure out what I'm talking about. So let me just sort of mention you can prove this using what's called Cantor's diagonal argument. Okay. And the idea with Cantor's diagonal argument is you actually show that you don't show that R is uncountable, you show that a subset of R is uncountable. And so if a subset of R is uncountable, then certainly R will also be uncountable. And the subset is the interval 0, 1. That's what Cantor's diagonal argument shows. It shows that the interval 0, 1 is uncountable. Okay, and the way the argument works is you show that any countable subset of the interval 0, 1. So you assume you have a list of these things, and you arrange your list in a appropriate way, and then from that list you construct a number which is not in the list, and so that shows you that any countable subset will exclude some number from the interval. Okay. All right, so that gives you some intuition about what countable and uncountable means. And so that gives us a way of thinking about what the dimension of a vector space is by talking about sort of the cardinality of its basis. Okay, and so a finite dimensional vector space will have a finite basis. You can talk about a vector space, and we will see examples of vector spaces with countable dimension, and then you have vector spaces with uncountable dimension. And we're not so much interested in exactly talking about the dimension of a vector space. We're mainly interested in the situation of whether a vector space is finite dimensional or not. Okay. All right, so that's how you talk about dimension. We should then talk about what it means for something to be a basis. Well, you know what it means for something to be a basis. You know that a basis is a subset of vectors that is linearly independent and spans the vector space. Okay. Now you probably only worked that out in the finite dimensional case where the basis is finite, but a similar characterization holds for arbitrary vector spaces. So let's see how that works. Okay, so let's let V be an F vector space. Okay, so I'm going to be talking about real or complex vector spaces here. None of this discussion really varies that much if you're talking about vector spaces over an arbitrary field, but let's be concrete. Okay, a basis, sorry, a subset B, let me not call the subset B, let me call it subset because B sounds like a basis and I'm not talking about bases yet. So a subset, let me call it lambda of V is linearly independent if for any finite subset V1 Vk of lambda, okay, and I, I'm going to ask my so I have a subset here, and so this subset, I'm of course I'm going to ask that this be a distinct subset, so none of these vectors agree with each other, of lambda is linearly independent. In the usual sense. And so what that means, you remember, that means if I take any linear combination of these finitely many vectors, like so, that implies that the coefficients must be equal to 0. Okay, and so this definition of linear independence boils down to the definition of linear independence that you know about already. The difference here is that this must hold for any finite subset. And in particular, the finite subset could have arbitrarily many finite, arbitrarily large, but finite number of elements in it, right? So there's no restriction on K. And one thing that's true, and you would have proved this in your linear algebra course, this definition of linear independence agrees with the usual one for finite dimensional vector spaces. So what am I saying there? Well, this definition places no restrictions on V whatsoever. And so if V is a finite dimensional vector space, let's say it has dimension n. So what that means is that it has a basis of n elements, okay? And so it's still going to be the case that a subset lambda of this n-dimensional vector space V is linearly independent if and only if every finite subset of that set, which is necessarily already finite, is linearly independent in this sense. Okay. So one direction of that is obvious. So if it's linearly independent in this sense that I'm defining here, then obviously it's linearly independent in the normal sense. And so it's the converse statement. It's not hard to prove. Like I said, probably you proved that in your linear algebra class, that if your set is linearly independent, then every finite subset is also linearly independent. Okay. Okay, so that's how you talk about linear independence in arbitrary vector spaces. Okay. Let's maybe look at some examples. Okay. And so let's take V equals Fn. Okay, and I'm now going to think about Fn as being isomorphic, as I had last time, to this space. Okay, now Fn, as we know, has a standard basis, and we know that that's linearly independent. Okay, so all I'm going to do here is I'm going to think about the standard basis in terms of this representation of Fn. Okay, so remember what that means. So E1 is the vector in Fn, which looks like this. E2 En. Okay. And so corresponding to, so these are vectors in Fn, of course. But now what I want to do is I want to think of these, this vector space is isomorphic to this one. So I want to ask the question, what are the elements of this vector space that correspond to that basis? So using the isomorphism, and I called it iota last time, so you can look back and remind yourself what that is if you forget. Okay, so this maps E1 to En to F1 Fn. So remember elements of, well, so actually, I guess because I'm starting with Fn here, I'm talking about the inverse here. So let me, sorry, let me go the other way. Okay, so iota went that way. The thing I'm actually interested in here is the inverse. Okay, so it maps the standard basis to elements of this vector space. And remember that elements of this vector space are functions, right? So the F valued functions on this finite set. And if you think about it for a second, it's pretty clear what these F's are corresponding to these E's. Okay, so Fj. Okay, so the jth element of this vector space. So that's going to be a function from the finite set 1 up to n into F. So that's going to be evaluated on a thing which looks like K. Okay, is going to be 1 when J is equal to K and 0 otherwise. Okay. So this is what the standard basis looks like when you represent it as an element of that vector space. So this is something that's going to come back to us later on. Okay, and so this set is linearly independent. Okay, so I could prove this directly, but I'm not going to prove it directly because I'm going to prove it in a more general setting in a second. But for our purposes here, it follows simply because this set is linearly independent, and this is an image of that under an isomorphism. Okay, and so isomorphisms map linearly independent sets into linearly independent sets. Okay. Let's look at another example, a more general example. Let's look at f to the j. Okay. So on f to the j, we're going to define, and so v is f to the j. Okay, let's define for j in j an element, and I'm going to call it fj, rather like I did here, because it's going to be the analog of what I did in this example here. So this is going to be fj is going to be an element of this space, f to the j. And so remember, all that means is that it's a mapping from j into f. All right, so I need to tell you what fj does. And it rather looks just exactly like that. Okay, so it's fj of k equals, okay, and so here k is 1n. All right, so here I'm going to have the same definition, 1 for j equals k, and I'm going to have 0 when j is not equal to k, and this is going to be true for every k in j, okay, because here j is equal to not the finite set, but some arbitrary set. Okay, and so this is exactly analogous to what I did up here, except there are not now necessarily finitely many of these vectors. There may be countably many, or there may be uncountably many, depending exactly on how big j is. Okay, so I claim that the set of these things is linearly independent. Okay, so let's prove this. Okay, so what's the definition of linear independence? Well, the definition of linear independence that I gave here is that I choose any finite subset and I show that it's linearly independent in the normal sense. Okay, so I take a linear combination of them, set it equal to 0, and then show that all of the coefficients must equal 0. All right, so I need to first choose a finite subset of these things. Okay, so a finite subset of these things will be associated with a finite number of j's, right? So I'm going to let j1 up to jm in j be distinct. So no two of them are the same. Okay, now, so that's going to give me my finite subset. And so what I need to do is I need to take a linear combination of those finitely many vectors and set it equal to 0. Okay, so that means C1 FJ1 plus C K F, sorry, I'm using M here. M F J M is equal to 0. Okay, now this is 0 here is not the scalar 0. It's 0 in this vector space. Okay, so 0 in that vector space simply means the 0 function, right? So because the elements of this vector space are functions. So it's the function which maps every element of J to the scalar 0. All right. Okay, so now what I do is I take this, and so this thing is now a function, right? These are functions, and that's a function, and these are, scalar multiples of a function, and then a linear combination of those. All right, so the point is the resulting thing is a function on J, on the set big J. So therefore, this thing is waiting to be evaluated on some element of the set J. And so what I'm going to do is I'm going to take, let's let L be any of my numbers 1 up to M. And what I'm going to do is I'm going to evaluate this expression by evaluating the functions on both sides, the 0 function here and then this function here, on the vector which consists of sorry, I'm going to evaluate each of these things on the integer, sorry, not integer, apologize. I'm going to evaluate these things on elements of J, and I'm going to choose a specific element of J, which is going to be 1 in the J elf component, okay, and 0 everywhere else. Okay, so I sort of muffled that a little bit, so let me write it down sort of clearly. Okay, so I'm going to go C1 FJ1 plus CM FJM. Now I'm going to evaluate that on, because remember this is a function again on J. Okay, so I'm going to evaluate that on JL. Okay. And this is equal to 0 of JL, because remember the 0 here is the 0 function. Okay, now good. All right, so 0 of JL is certainly 0. That's the definition of the 0 function. Now, what about this whole thing? Okay, well, what are these F's defined as? Well, they're defined like so. And so I know that when I stick JL, and now I'm going to use the definition of addition, scalar multiplication, and you kind of expand this definition, this thing out. So let me maybe do that just so it's clear what we're doing. So we're going to go C1 F J1 of JL plus CM F JM of JL is equal now to the scalar 0. Okay, so now we can easily see what's going on with this sum because of the way that these vectors are defined, like so. There's only one term in this sum, which is going to be non-zero, and that corresponds to the JL term in the sum, right? And so the point is that this implies that CL FJL of JL, which is just CL, is equal to 0. Okay. All right, just by the definition here. All right. And so that shows the linear independence that I want, right? Because this is now true for every L. You can do the construction I just did for any L. Okay. Oops. Okay. Good. So now we have a specific example of an infinite linearly independent set, okay? Because if this set J is infinite, then there's infinitely many of these vectors, okay? So this is sort of how you can check linear independence for an infinite collection of vectors. Let's look at another example where we can do that. So here we're going to take V to be the vector space of continuous functions on the interval 0, 1 that we talked about last time. And here I'm going to take the functions Fj of x is going to be the function, let's say, sine 2 pi j x. Okay. That's certainly a continuous function. So what do these functions look like? So these are functions defined on the interval 0, 1. So f1 is just the sine function with period 1. Right, so that's f1. f2 will be the sine function with period a half, right? So it's going to look like, if I can draw it without making too much of a mess out of it, it's going to look like that. Okay, so this is f2, and so on. Okay, so I claim that this infinite collection of functions is linearly independent. Okay, so I'm going to use a strategy a little bit similar to this. I'm going to choose some finite index set of now my vectors are indexed by the set of positive integers, and I'm going to write a linear combination, and then I somehow have to show, like I did here, the coefficients are 0, but here it's a different kind of a trick. Okay, so let's choose a finite subset. So J1, Jm, be distinct. Okay, so then I'm going to write a linear combination of these sine functions and set it equal to 0. So I'm going to go C1 Fj1 plus Cm Fjm is equal to 0. Okay, with these f's. All right, so again, these are functions, right? That's the 0 function, which is a continuous function on the interval 0, 1. These are the sine functions of the appropriate period, and then I'm taking linear combination of them. All right. And so let's just sort of write some things down that immediately follow. So I must have that C1 sine 2 pi J1 x plus Cm sine 2 pi Jm x is equal to 0. And this must be true for every x. All right. And that's just because this is the 0 function over here. Okay. All right. And I'm also using the definition just like I did up here. In going from here to here, I use the definition of scalar, in going from here to here, I use the definition of scalar multiplication. I'm doing that here as well, in going from here to here. All right. Okay, so if there's the 0 function, so this is two different representations of the 0 function, kind of a complicated representation over here, and then the 0 function over here. But certainly it's going to be true that if I take the 0 function and I multiply it by any other function, I'm also going to get the 0 function. And so I'm going to choose as my function. So I'm going to do the same thing as I did above. I'm going to let L be one of these indices from 1 to m. Then C1. So I'm going to multiply the 0 function, okay, and the 0 function in these two flavors, that flavor and then that flavor, by the function sine 2 pi JL, okay, sorry, L on both sides, okay. So it's sine 2 pi J1 x sine 2 pi j L x. And I have m of these. And that's still equal to 0. Okay. Now what I'm going to do is I'm going to do another calculation on this. And the calculation I'm going to do is I'm going to integrate. Okay, so I have the 0 function again. Here I've just taken the 0 function and made a more complicated representation of it, but it's still the 0 function. And that's the 0 function. So I'm going to integrate now between 0 and 1. Okay, and so here I'm going to be integrating the product of these sine functions. Okay, and we're going to use a fact here about that integral. You can do that integral yourself, of course. You know tricks for doing integrals, so use those tricks. And the punchline is this: the integral from 0 to 1 of sine 2 pi m x times sine 2 pi n x dx. Okay, so n and m here are integers. That is equal to 1 if n is equal to m and 0 otherwise. Okay. All right, so I'm not going to sort of write out the integrals for all of these terms. I'm just going to sort of chat my way through what happens here when you integrate. So when you integrate, so we have JL here and J1 here. And so when you do this integral, you're going to either get 1 or 0, depending on whether L is equal to 1 or not. And similarly for all of the terms. And the point is you end up with exactly the same kind of thing that happened up here. Okay. Okay. And therefore, after integrating, what you get is you get that CL is equal to 0. Okay. Because you're only going to get one term, one of these integrals. When you do the integrals in this expression up here, only one of them is going to be non-zero, and that's going to be the case when the JL appears in both terms. Okay, so you're going to get CL is equal to 0, and so you're done. Okay, so that is linear independence. Okay, so this is a way of talking about linear independence for arbitrary vector spaces. And we even have a couple examples of vector spaces which have infinite linearly independent sets. Okay, and so next time what we'll do is talk about the other property of a basis, which is the spanning property. Okay, all right, so that's next time.